First of all, I would like to thank the organizer for giving me the opportunity to speak in this conference. And I'm going to present a joint work with Luis Ugarte from University of Zaragoza, where we work on the study of some pseudo-Riemannian manifolds on complex manifolds. So although we have already heard about complex manifolds in the last talks, I would like to give some basic notions so that you can understand better the problem of the small deformations and so on. So the way we define a complex manifold is just similar to the one of a differentiable manifold, but as you can guess, we need that the chart go to Cn instead of Rn, and we also need that the change of chart is holomorphic and instead of differentiable. So there is an obvious relation between complex manifolds and differentiable manifolds, because when we have a complex manifold of complex dimension n, the same topological space has the structure of a differentiable manifold of real dimension twice the complex dimension. Because for every complex chart, we can separate the real and imaginary parts, and then we get a real chart. So the natural question is what happens with the other implication. That is, once we have a differentiable manifold of even real dimension, when we can build up a complex manifold. So this question was answered by Nylander and Nirenberg, who characterized complex manifolds as pairs in J, where M is a differentiable manifold of even dimension, and J is what we call a complex structure. A complex structure is just an endomorphism on the space of smooth vector fields on the manifold, satisfying two conditions. The first one is that the square of J equals minus the identity. So one can think that we want J to imitate the imaginary unit. And the second one is the value of this tensor here, which is called the Eigenhuis tensor. So when we have these two structures, then somehow I think that J is telling us how to organize the real chart to find a complex one. This would be the idea, rough idea. So the important thing about this is that given a differentiable manifold M, we can endow it with different structure as a complex manifold, just changing the complex structure, this one here. And related to this comes the idea of holomorphic deformation. We fix a compact differentiable manifold of even dimension, and we consider on it not just one complex structure, but a collection of complex structures which are parametrized on a disk. This one. So the real manifold is always the same, but we change the complex structure, and thus we get different complex manifold. We can be thought that they are close to each other because the complex structure are close to each other, let's say. In general, we assume that the disk is centered at the origin in C, and we usually say that XT is a small deformation of the central point. Okay, so given a complex manifold which satisfies a certain property, which might be either the existence of some metric or some cohomological aspect of it, we say that the property is stable when we consider a small deformation, and when one point here in our disk satisfies this property, then any nearby complex structure also satisfies the same property. Okay, so when this holds, we say that the property is stable. But this should hold for any holomorphic deformation we can think about. Okay, so in our case, we would like to deal with this problem of holomorphic deformations, paying attention to the existence of neutral Calabi-Yau metrics. So before to explain what is a neutral Calabi-Yau metric, I would like to give some other ideas on complex geometry. Some few facts that I will need in the following. So the first remark is that my complex structure induces a bigraduation on the space of complex forms, because this endomorphism on the space of smooth vector fields on the manifold can be equivalently defined on the space of smooth forms, one forms on the manifold, that's following this definition here. But then, if we complexify the space of one forms, it turns out that this map splits my space into two eigenspaces, one associated to the eigenvalue I, and the other one to the eigenvalue minus I, which are defined in this way. Okay. And then this regraduation moves to the space of complex K forms. So every K complex K form would be of particular PQ type. And then the second remark is that my complex structure decomposes the differential. One should recall that the space of forms on a manifold is a differential graded algebra which has a wedge product and a differential, which sends a K form to a K plus 1 form. So if we complexify these spaces, then as this space here splits in this way, we can focus on a particular B degree and think where this differential sends my form inside this other space. And it turns out that when J is a complex structure, the specific degrees are these ones here, which allows us to split our usual differential into two differentials, which are del and del bar, we usually call them, which are defined in this way. The good point about these two differentials is that we can define cohomologies specific of complex manifolds and differential to the usual Laurent cohomology. Different, sorry. So I'm going now to metrics. So given a complex manifold, as seen then as a pair MJ, where M is a differentiable manifold and J is a complex structure, our differentiable manifold can be endowed with a pseudo-Riemannian metric. Apparently, these two structures might be independent to each other. So we would like to define some kind of interaction between them. And so we introduce this compatibility condition. The good point about this compatibility condition is that when we plug J on the second component of our metric, this gives us a 2 form, which is known as the fundamental form, because there is a one-to-one correspondence between my fundamental form and my pseudo-Riemannian metric, just using my complex structure. Indeed, with respect to the bigraduation induced by my complex structure, this fundamental form is a specific B degree 1-1. And moreover, one can check that the signature of my pseudo-Riemannian metric is of this type. Okay. So once we have this, we want another condition, which is this one here. We want that the fundamental form is closed, because then, apart from the pseudo-Riemannian metric, we also have a symplectic structure. In the case where my metric is actually positive definite, we are in the world of Keller geometry, and otherwise, we are talking about pseudo-Keller geometry. So why am I talking about pseudo-Keller manifolds? Because neutral Calabi-Yau, I'm going to skip this because I'm running out of time, are a special type of pseudo-Keller manifold. The starting point is similar to a pseudo-Keller manifold, but we need to impose some extra conditions which are these ones. First of all, I need that the complex dimension of my manifold is even. So the real dimension would be a multiple of 4. And we also need to find a form of B degree 2 and 0 that now we're vanishing, which is parallel to with respect to the Levi-Civita connection of my metric. So once again, when G is positive definite, then we talk about neutral Calabi-Yau geometry. And when we focus on this signature here, neutral signature, we can talk about neutral Calabi-Yau structures. So what happens with the stability of these structures? Concerning Keller-Calabi-Yau, it was shown by Bogomolov and Todorov that this property is stable. That is, if I start from a Calabi-Yau manifold and I deform the underlying complex structure, then I will be able to find another Riemannian metric which is compatible with my new complex structure and which will give rise to a symplectic form and with all the other conditions. This one condition will also hold, right? So for this reason, we wonder what happened with neutral Calabi-Yau. What happens when we weaken the positive definite and we focus on neutral signature. And the first thing we saw is that when we deal with neutral Calabi-Yau surfaces, they are stable. The result comes combining some previous result of Telemann with one result we had about the stability of pseudo-Keller manifolds when this number here, which is related to bottom cohomology, remains stable along the deformation. In this case, one can ensure this condition when we deform the complex structure of a complex surface, and we are able to show that these neutral Calabi-Yau surfaces are stable. However, when we go to higher dimensions, we were able to show that the property is no longer stable. To do that, we focus on the manifolds, which are quotients of nilpotent Lie groups by appropriate lattices. And we found a manifold which was neutral Calabi-Yau, but whose deformations were not. So this would be, so we constructed this 8-dimensional nilpotent Lie algebra, and we found a complex structure, and indeed we found a whole family of pseudo-Keller metric. But among these pseudo-Keller metrics, we realized that some of them were neutral. And indeed, the last condition, which was this form, which was parallel with respect to the Levi-Civita connection, we could also find it. That's proving that our manifold was neutral Calabi-Yau. But then we deform the complex structure of our manifold. This is kind of easy to do, let's say, on the manifolds, because one defines a base of 1-0 forms starting from the original one, and one needs to deform these bases along a Dolbeault cohomology graph. And for 10 previous results, you know that you are not, by doing this, you do not change the underlying real manifold, but you do change the complex structure. And as you can see, you get a new set of structural equations that when t equals 0, one recovers the initial one. So that's why we are able to see somehow that this is a good deformation. And indeed, what happened is that this deformation here did not have any pseudo-Keller metric. So this allows us to prove that the non-stability of this property. And by taking products back to right, we show that this non-stability goes indeed to higher dimensions. not just particular of complex dimension 4. So I will stop here and thank you for your attention.